everyone, my name is Pingbang, and today I'm mainly focusing on two papers, but in total I will cover four. And yeah, let's just see. So basically, the motivation of this meeting is throughout the entire reading group. Usually, the setup of data attribution is kind of well specified. So, for example, we like typically know what the task is, what is our training algorithm, etc. And but in this talk, at least the four papers I choose, I try to make them kind of like under the same theme. So here I'm trying to focus on like data attribution or data evaluation method. They are somewhat agnostic. So firstly, we'll focus on large language model pre-training, and we will cover two papers for this. And the first one is like kind of the um kind of the preliminary or um yeah, just get started. So it's will not be any kind of agnostic, but the second one will be. And the second one will be like downstream task and agnostic. So for the second paper, we really don't know what downstream tasks are. So, and in this case, we are still trying to do data attribution for that, which is kind of interesting. And then we'll jump to another paper that is focusing on learning algorithm agnostic. So for that, we kind of know the task, but we don't know what learning algorithm we're going to use to train the model, which is also interesting in my opinion. Yeah, so this is the general plan. As Jiaqi mentioned, we'll first talk about tracing, which is very traditional and well-known method, but somehow we omit it in our reading group. And then we'll talk about pre-training. And interestingly enough, on the two papers I'm going to talk about kind of all rely on tracing to some extent. And then we'll talk about the learning algorithm agnostic paper, which is called LAVA. So this is four papers we are going to talk about. And just yeah, so a remark here is I will try to follow each paper's own notation. So I will not try to unify them in this presentation just to yeah, just for your convenience. So if you are interested in any one of the papers I talk about this in this talk, you can just go back to the paper and follow the same notation. Yeah. So let's get started. So first we're going to talk about tracing as I mentioned. And the setup is follow. Consider a space of examples and echo in that. And this is the space. So small z is individual training examples. And I will put a prime to indicate that it is a test examples. And here test doesn't really mean like the testing data set, but really is we're trying to attribute a particular, let's say, prediction of z prime back to training samples z. So this is not necessarily used as like test data set in traditional machine learning. And then specifically, we'll use S for training point. So S is just a subset of Z, and we'll consider like label them as Z1 to Zn. And additionally, we'll use W to parameterize the model, and that is the model weight. And we'll use small l as a loss function, which takes in like model and one training samples and outputs some real number. And we further assume that the model or the W, the weight, is trained by empirical risk minimization. So let's say we are stochastic gradient descent. And under this setup, the goal is quite simple. The goal is just to define some notion of influence or attribution that can somehow track the training dynamic. Okay, so if we recall previously, um, the most well-known one is influence function, which only care about the final model we get. So no matter how we get there or how we get that model, the attribution will be the same. But here, if we kind of take different routes or different initialization, and somehow we end up with the same model, the influence or the attribution we will get is different, which is kind of also important in my opinion, because training dynamic sometimes is like intuitively it contains more information than just the final model. Okay, so this is our goal. And let's see how one can do this. And actually the example or the idea behind tracing is very simple. Let's consider the very ideal case. So let's say in each SGD update, we use only one training example. And let's say at iteration t, we use ZT in our training set S. Then the natural way to kind of trace the influence of this training example Z, given a test example Z prime, is basically just, okay, let's look at all the iteration where we actually use this Z as our training sample, as our in our SGD update at iteration T. Then we just see, okay, how this Z influence the loss change. Okay, so the loss here is evaluated at the test example Z prime. And here I put a small footnote indicates that, okay, Z prime can also be S. So maybe I'm also interested in evaluating what's the or attributes. Sorry, somebody's not muted. Okay. Yeah, so maybe we can also be interested in attributing some other training sample back to the whole training set. So Z-prime can also be in the training set as well. Okay. So I think this is all fine, right? The ideal version. The basic idea is just, okay, we trace the loss change among each iteration. Okay. And the remark here is, if we look at the total loss difference, and here I put capital T to indicate the final iteration. And if we look at the total change in loss with respect to Z prime, it is just all the influence or tracing influence summing up over the training set. Okay. And okay, this is quite nice and very natural to define, but there are some problems. The first one is this ideal version is kind of computationally heavy because, okay, we probably need to recall all the weights and we need to evaluate for every model weight in each iteration, what is the loss? Okay, this is one. And the second one is the assumption is not really valid for any modern training paradigm. So in modern training, we'll typically use mini batch. So like one simple, like very naive way to do this is probably not very suitable. So how to mitigate this is very simple. To solve the first problem, we basically use first order approximation as usual. So let's say we still not care about the mini batch issue. So we still consider like batch with size 1. So each batch I call it capital BT, and it's like includes a singleton, one single training example. Then the weight change via SGD update is just this, right? And if, okay, so A.C here is the step size, right? So if the step size is very small, then we can basically just do a first order Taylor approximation around the loss, and we'll simply get this, right? And if we combine these two, we see that, okay, we can substitute WT plus 1 minus WT back to here. Let me draw something. I can substitute this. Let me change. Substitute this into here. So I replace this into here. Then we get this, right? Get this. And What does this mean? This means for tracing, because at every or in the formulation of tracing, we only care about the loss difference. So if we kind of manipulate this term and I bring this back, I get this expression, and I can just use this in our tracing formulation, and we get kind of the first order approximation version of the tracing ideal. Okay, so this is the first step. And the second step is also easy. That is, if we kind of want to extend the setup to handle mini batches, then the first observation is when we do the same first order derivation, the gradient for a single batch, which can contain more than one data point, it would just be like 1 over b over the sum over the gradients. So nothing fancy. And the idea is, okay, so since the gradients for that mini batch distributed naturally or decomposed naturally into every examples in the batch, then I can just attribute this gradient by looking at individual gradients, right? So this is exactly what we did. So intuition is, okay, for each z in this batch, we attribute this much as the influence. Okay, this here missing and nabla, but it's fine. So basically what we did is, okay, we ignore this summation and we just care about, okay, for every z in BT, we attribute this much as the tracing influence. And what we did is, okay, we then look at every t such that, okay, so if we are interested in one specific training example, look at every t such that that batch actually contains that particular training point z, and then we're done. So basic formulation becomes this, right? So we look at every t such that this training example actually is contained in this BT, and um for that iteration, how many influence we attribute? We attribute this many, right? 1 over b times this. And the remark is, yeah, so basically this is the whole thing or the whole pipeline for tracing. And several remarks can be made here. The first one is this really doesn't rely on any optimality condition. So as you can see, we can stop anywhere we want. So we can say like capital T is we run it for 10 iteration. We'll still get something kind of meaningful. And the second remark is um, it's probably not very practical to consider all iterations. So what people do is we consider checkpoints. So let's say we consider the initialization, the 10th iteration, the second or the 20th, and the 100th, and etc. And we can also do this like summation. And the extreme case is just, okay, we consider one single checkpoint, that is the final checkpoint, when t is the capital T, and it will just like correspond to this. And this basically recovers the single gradient dot method. Right. And we assume that, okay, for the final checkpoint, kind of the mini batch contains z in some sense. But the idea is you can take the checkpoints version to the extreme and we consider like very few checkpoints. And in some sense, it recovers the simple gradient dots. Like we just take the gradients of the test points and the training point. Yeah, so that's the whole idea of tracing. Any questions? Because the like next two papers, well, I'm going to talk about that is going to rely on tracing. Okay, so if not, then we can jump to the large language model training. And the first thing is, as I mentioned, the first paper will kind of be we know the task, the end task for the training. So the second one will be, okay, we don't know the end task, so what can we do? So let's see the first one. And the setup is as follows. So here, because we are considering large language model pre-training and also the fine-tuning or end task, so we naturally have two different training sets. One is the pre-training one, and usually we don't have any annotation for the pre-training corpus. And here I use P, ZP to stand for pre-training. And I use ZT for stand for end task, so T here for task. And for that, we typically have annotation for the training data set for end task, right? So that's the setup for the data set. And for the model, we consider the decomposition as follows. We have kind of the feature or the, let's say, encoder, and we have the head that is kind of the decoder. And the feature is kind of general enough to be transferable. So let's say I train a large language model on pre-trained corpus, and I can use it for different tasks, different end tasks. So it's kind of transferable. And for the head, it is not transferable, and it is like task specific. And they are parameterized by theta and phi, respectively. And also we consider loss function for pre-training. So here, I think the author is kind of being sloppy. And yeah, I would say the condition and the setup is not very well defined in some sense. So I will skip this through or skip these papers um, through. Yeah, so anyway, let's see. So they say that, okay, we have the loss function for pre-training defined as follows. So I think what they mean is for the pre-training, we're not merely pre-train for like general feature, but we have some sort of task in mind. And for the end task, we then fine-tune to get the different head. Okay. So here the theta are kind of fixed, but the head is different. And then we further assume that models are trained by also empirical risk minimization, which is also not very well specified because according to their paper, they say that their model is trained by using this. And it to me it's kind of odd, like they are mixing two laws together. And yeah, anyway, they're claiming this, like their model is kind of trained by ERM. Okay, so with that kind of caveat in mind, the overall goal is the follows. Under this setup, we kind of want to select information points from the training or sorry, from the pre-training corpus, and then we can perform efficient pre-training using only the selected data points. And the overall goal is, okay, maybe we can use few pre-training corpus data points, and then we'll achieve high end task performance. So the overall setup is like, okay, we know the end task, and we have the pre-training corpus at hand, and we kind of select few of them to do pre-training and then do fine-tuning. And we hope that only using few pre-training corpus data sets, we can achieve high end task if it performance. Is the goal clear? I think the setup is really messy and they are not being very clear for this. So yeah, so I'll probably just skip this through very fast. Okay, so what they propose is this. The key insight they have, at least they propose, is that the pre-training sample ZP can only affect prediction of an n-task sample ZT by influencing theta, by influencing the feature model only. So we cannot affect the prediction of ZT by influencing, let's say, phi t, right? So because basically when we train on the when we train, we don't really know what ZT is. We only know kind of roughly the task. So that's the basic intuition that have like we don't really know phi t at hand or beforehand. So we can only affect ZT by influencing theta. If we have this intuition, then basically from their setup or from their assumption, you can do standard influence function analysis, and then we obtain this. So the idea is very simple. We do the same influence function, and then we arrive at the similar influence according to influence function, with a caveat that we are only looking into gradients with respect to theta, but not phi or theta and phi. Okay, so that's the I would say the only um novelty, I guess, for this. So we just note that we can only influence this by influencing theta. So if we have that, then the gradient should only with respect to theta. And the author said, okay, this is very expensive to evaluate for a large language model. Sure. Then what we do is we do tracing, or actually we do gradient dots. So the whole thing becomes this. And this is just a tracing, but now the gradient is with respect to theta only. Okay. And yeah, so that's really is what they are doing. So they propose to use gradient dots with respect to only the feature parameters. And this is what they eventually do. They first compute the gradient dots influence and select, let's say, top k influential points from the pre-training corpus, and then they use pre-train this top k training set to pre-train and then fine-tune. So the overall experimental result we have is a newly pre-trained model using only 0.45% of the data outperforms the basic pre-trained model using every pre-training corpus. Okay, for numerical standpoints, this kind of is impressive, I would say, but there are several weaknesses. The first one is, okay, the notation is not very clear, so I would doubt that's the overall theoretical uh, rigorous for this work. And the second one is it's kind of questionable whether this is very practical because, okay, so to perform this, you really need to first pre-train some model to do this, right? So what's the point if you have already a pre-trained model and then you select some small training set from that pre-train and you re-pre-trained another model and then do fine-tune? I would doubt the practicality for that. But overall, this is the first work. I think there's like not many things to talk about for this. So, but I will still take questions. Okay, if no, then I will just jump to the second paper, which I think is much more interesting and insightful. So here we are going to again mention the setup and notation, but here the setup is kind of similar, or the notation kind of similar to the tracing paper. So again, we use Z for the space of examples, and we use like small z as training examples and Z prime as task examples. But here we use theta as the weight. Sorry. And then we use loss L as the loss function. And the goal here is to propose a model-driven reweighting algorithm for pre-training data. So what does this mean? This means, okay, although we don't know what's the end task we're going to do, but at least we know what kind of model we're dealing with. We're dealing with language model. And the whole insight of this paper is we leverage several facts about language model, and then we perform data attribution with this knowledge, although we don't know the end task. Okay. And to explain the paper title, the paper is called like presence. It is because we are going to rely on something called self-influence. And if you write everything down, it's like pre-training data reweighting with self-influence. So presence. Okay. With that in mind, probably I can first introduce what is self-influence. And also we are going to use tracing for particular. And here I'm going to use actually gradient dot for the final model. So it should be familiar. And actually, self-influence is just, okay, we're not going to use any z prime, but we care about z here. So we care about what is the influence of this training sample z with respect to the test example, also z. So this is why this is called self-influence. We're kind of attributing the prediction or the model behavior of this training sample back to the training sample itself. So self-influence. Okay. And why is this useful? This is useful because the author noticed something that is interesting probably only holds for a language model. That is, the self-influence correspond directly to sample quality when training language model. So intuition is the follows. Bad examples tend to have high self-influence, and this is because they reduce the loss when we're at somehow good models already. So let's say at iteration t, the model is kind of already well trained, and suddenly it is like the model sees a, let's say, bad outlier or a malicious flipped labeled training samples. Then the model will try to adapt this new knowledge, like wrong knowledge. So the loss will suddenly drop because it kind of knew or learned new things, which is not something the model is expected to learn because it is wrong or bad. So this is the basic intuition. And authors actually conduct several experiments to demonstrate that, okay, this is actually a real phenomenon. Okay, so let's see the figure. And focusing on the left-hand side, here we have clean text, namely the language or the training corpus is just as it is. And the second one is the noisy text. And what the author did is they kind of shuffle the text in the training corpus to make it like basically nonsense. And we noticed that the self-influence score or the self-influence for the clean text is significantly and like consistently lower than the model trained on noisy tasks. So the self-influence for model trained on noisy task is significantly higher than the model trained on clean task. Okay, so noisy task, bad examples, and have like high self-influence. So
Timon,
this is one evidence. Okay.
yeah, sorry. Can I ask a question here? So, for this two setting, what is the model used to calculate this self-influence score?
Oh, okay. So I think they use something. Let's see. Um, I cannot kind of remember the model's name, but um, let's see. I think
Oh,
they
I
are
mean,
using.
I'm not asking like
Oh, okay.
the exact like model architecture or something like that, but I'm just wondering. Okay, so basically, By what model, I mean, what's the training data for the model they used?
Oh,
For the,
okay. So I think they use, okay. So they at least for the left-hand side,
um,
the blue dots correspond to English text,
um,
and other are to other languages. And I think they focus on like kind of like um query and answer data set. So like they have like some sort of like query answer
I see.
pair of text, and they are like having several languages.
So, I guess my question is like, I think there are two ways you can do this, right? So one way is you train a model on whatever data, and you just fix that model, and you
Oh, no,
can
no, no, no.
calculate
Okay. Okay, I see,
self-influence
I see.
for different for different corpus using the same model, or like you train the model on each of this
Right, right, right.
corpus, and then calculate the self-influence on this corpus.
Yeah, got it, got it.
Okay,
Yeah, so basically they train the model on the like shuffled text
okay,
for the bad model.
I see.
Because like for tracing, okay, maybe I'm not being very clear. Actually, we are not exactly using gradient dot, but um we somehow care about the training dynamics.
Oh,
So
yeah,
we
yeah.
actually like take into account when we calculate self-influence. I will show that later.
Mm,
But yeah, so we are directly trained on these bad examples.
yeah, makes
Yeah,
sense.
the same thing at the right hand side. So the right hand side is about like auto domain um experiments. So here the blue correspond to in-domain samples, and other two are kind of like domain specific training examples. And they are still correspond to okay. Okay, for this, maybe they are using different evaluation. So maybe they are not exactly trained on physics and chemistry when they are training. But when they are evaluating, they are evaluating at physics and chemistry. That is kind of out of domain test examples. And they observe like this. Yeah, I may need to double check this, but I think the basic idea is bad examples lead to higher self-influence score. That's the high level idea. Okay. Yeah, so if we have that intuition in mind, then a very natural way to do like attribution or um using the tracing attribution to do better pre-training is using the follow paradigm. So the idea is really to filter our highest self-influence score data with respect to some proxy model. Okay. Because, okay, so you are talking about we're going to pre-train based on some data set that is after the attribution. So then naturally we may want to have some other proxy model, and then we can use that to train a properly pre-trained model. So that is what the author did for this one. So the basic idea is this. We randomly sample some uh, corpus or pre-trained corpus to train a proxy model and what I call scoring model. And then we use this model to do the self-influence score. Okay. Then what we did is, okay, we just sort the score. We filter out the high self-influence score data. So we like presumably um only gets like high quality data for the actual pre-training. And then we use them, the low self-influence score data to pre-train the final model. Okay. And for this is probably a minor point. For efficiency, also proposed to only consider the first layer of the decoder and the first layer of the encoder um, when calculating the self-influence score. So like this is just some facts about tracing, because you can basically decompose it into layers. And yeah, that is what they also did. They only look at the first layer of the decoder and the first layer of the encoder, and they think these two layers already provides good enough information for self-inference score, and provides like good enough information of distinguishing good and bad training samples. Okay, is the pipeline clear? This is what I call present sequential, because we are kind of doing a sequential workflow to finally arrive at a pre-trained model. Yeah,
Sorry to interrupt. Yeah. So they already trained like a proxy model, and I assume that it is like much smaller than the original
right,
model.
true.
And they
Yeah.
are even like doing more aggressively, like only like considering like on 2 layers in that small proxy model to compute the tracing score.
Right, I think so.
Okay. Okay. Yeah, I'm just thinking like if proxy model is like small enough, why they still
Okay,
using this?
so basically their hypothesis is, for smaller model, it can already captures, like based on our intuition, like when it sees a very bad examples, then the self-influence should be high. So if we have this intuition, and we hypothesize that this intuition also hold for smaller model, then only training this smaller model suffice for identifying like highest self-influence score data points. So you can already like distinguish good and bad training samples. And then we use that information to pre-train like probably larger and better model, right? So
I agree. But I'm asking like whether why they're using like on decoder and encoder layer, because is it
oh,
like
okay.
merely solely for computational efficiency, or
Yeah, I
there's
think
other
so.
reason?
I think so.
Okay.
They don't have like much explanation for this. Like they didn't explain like why they choose these two layers. Probably it is because some ablation study, but
Mhm.
I'm not really sure. Let's put it in this way.
Okay. Yeah, sure. Thank you.
Sure. Any more questions? If not, then I will jump into the experimental result for this present sequential. Okay. Yep. So using the filter our data set to pre-train the model, then we kind of obtain a consistent improvement. So let's see. So here we have like question answering data sets, sentence pair, structured data set, and yeah, basically all the metric is it is probably not very important to understand every metric, but it's just like higher the better. And then for the first experiment, they are considering like cross-lingual linear shot transfer, and they compare the baseline, the base model, and the baseline with the present sequential pipeline. And then, interestingly enough, they also do present sequential reverse. So basically what they did is, instead of choosing the low self-influence score, they choose high self-influence score and see, okay, whether this is really the case. Like high self-influence score indicates bad examples. And we see that, okay, for the like normal sequential, it actually improves among every experiments compared to the base. While for the reverse one, it is worse among every experiments compared to the base. So it kind of also validates our intuition, right? And the same thing basically holds for the second experiment, like the translate train. So basically the models is fine-tuned on English data plus translation in target languages, and we're interested in translating. And also sequential outperform base, and the reverse is worse than the base. Yeah, I think this is not as much to explain. It is basically just validates our intuition and the pipeline's effectiveness. Yeah, so this is for the sequential. And the very natural question you might ask is, okay, so this seems very nice. And as Dingwei said, do we really need to train a single scoring model? Probably not. We can do something like Clever. So this is what they propose to do, like presence without the sequential. So kind of do this high self-influence scoring at like in an online fashion. So the basic intuition is this: we can calculate the self-influence score at each training step, right? Then there's nothing stopping us from doing this. And if we have like the self-influence score information, then probably we don't necessarily need to discard based on some, let's say, threshold. Maybe you can do that, but maybe a clever way is to weight them with respect to the self-influence score. So more formally, let's say given a batch V with consists of like n data points, we can compute the self-influence score for OI. And here we're still caring about like the first layer of the decoder and the encoder. Okay, I will omit this for now. And then what we do is, okay, we compute the weight based on the self-influence score. Okay, so self-influence score can range from like, let's say ideally minus infinity to plus infinity. So how can we weigh them? Probably the most natural thing is to do a softmax to normalize them into like a probability. So you sum all the weights and then it becomes one, right? And interesting enough, we control the softmax computation by a temperature. So this will become kind of important, but we can neglect this for now. So basic intuition is, okay, we somehow weight the self-influence. Okay, so, sorry, we somehow weight the training point by the self-influence. And how we exactly do this? We weight the gradient, right? So if you want to do some gradient updates, then the most natural thing for you to do is you reweight the gradient when you calculate the overall mini batch gradient for this batch. Okay. And here comes like another, I would say, insight for a large language model. That is, the author noticed this, I would say, observation. Like the basic intuition is training loss decreases exponentially early in the pre-training. So what does this tell us? It basically tells us that if we have high self-influence score along the training, like at every step we calculate the the self-influence score and we see that it is high, but this step is early in the pre-training, then it is kind of natural, right? Because like in general, it will happen. So it does not necessarily mean that high self-influence score early in the training indicates bad examples. Okay. And coming back to the original intuition, for well-trained models, it's probably not very good to see how high self-influence score, right? So we have kind of a two-stage pre-training we can do. Or we can kind of divide the pre-training stage into two stages, and then we do reweighting in two different fashions. So why exactly are we going to do this? So let's say in early stage in the pre-training, we know that, okay, high self-influence score actually kind of important because it is natural. So what we do is we let the temperature, we call it temperature, tau here. And if tau is greater than 0, then it will not flip on the self-influence score, right? The sign will not flip. So if self-influence score is high with positive temperature, it will still be high. So we can use positive temperature to puts more emphasis on high self-influence score data points. So it will drives the model learning and promoting novelty. And in later stage, when the model stabilizes, then we put a negative temperature to flip the sign of the self-influence score. So in the later stage in the pre-training, a data point with high self-influence score should receive lower weight. This is done by like negative temperature. So intuitively, this is like just based on this two intuition, like early in the stage, and this is for later in the stage. So we kind of do this two-stage strategy. Any question here? So this is basically the whole proposal for the presence. Like we can calculate the not high, but self-influence score in a online fashion. And then we leverage the model insights. We know that we are dealing with language model. And if the language model receives high self-influence score early in the stage, then that data point should like should be promoting novelty. And if we see high self-influence score later in the stage, then we kind of hypothesize that this might be a bad examples. So this is what we did. Any questions? If not, I'm going to present the experimental results for presence.
I've been back. One more question. So how they divide these two phases?
Oh, okay. So I think they do heuristic. I see. Okay. The loss sounds threshold, and okay, let's switch to negative temperature. I think that even cruder, they are not actually looking at the loss. I think they are looking at the iteration. They just say, okay, after this iteration, I switch to another tau. So they
like
are
predefined.
Right.
Okay.
They are not doing this clever. They are just like heuristic.
Yeah, thank you.
Any questions? Okay. So here is the same experimental result compared to the previous one, but just now we are using presence. And now we are not unfortunately we don't have like presence reverse. So we don't only have like base and base plus presence and a larger model plus presence. And like still the basic trend is with presence, it helps in every experiment, like regardless of the base model or the larger model. Okay. And probably you are wondering, how does presence and presence sequential compare to each other? Because if you think about this, presence sequential kind of have more information, right? Because it sees every data point beforehand. Unlike presence, it's trying to decide at every step. So it may like, okay, so if it's made some mistake early in the stage, it's impossible for the pipeline to fix it later in the stage because the decision is already made. Or you can think about this as online problem is typically more difficult than the offline version, and sequential is kind of the offline version of presence because we already gather all the information we need beforehand and we do self-influence filtering. But actually, we observe that they are kind of comparable, and in some cases, presence outperforms presence sequential. And also basically hypothesize that, okay, this is maybe because the presence is like more adaptive, right? Like it can adapt the intuition we have on the two different stages, while the present sequential doesn't have that intuition. or does not exploit that intuition. Yeah, so that's the present versus present sequential. And I'll probably conclude this paper by mentioning this. So also validates the two-stage behavior by the final control, because like previously we are saying that, okay, later in the stage or higher self-influence score correspond to bad examples, but we don't really know, okay, whether the another intuition we have, that is higher self-influence score, do promote novelty early in the stage. So this is what the author did. They also did an ablation study on if we kind of play around with the sign of the temperature in the stage, what will happen. So here present D is like direct. We use 1 throughout the training, and R is inverse. We use -1 throughout the training, and ID is inverse 2-stage. We first put negative sign, or you use negative temperature early in the stage, and then we use positive temperature later in the stage. And we see that basically if you reverse it, it becomes pretty bad. While if you only use inverse, it sometimes will help, which is kind of interesting. But at least if we stick with our original plan, that is +1 early in the stage, -1 later in the stage, it is somehow comparable to all the like best performance. But yeah, basically for the trend to hold true, maybe it's better to look at the second experiment. Like if you reverse it, it will decrease. Right? Let me draw something. If you reverse it, it will decrease compared to this, compared to this, and compared to this. Yeah, so okay, for the first experiments, this trend might not be very apparent, but I think the second one explain this two-stage phenomenon actually exists.
So it's actually not like all decreasing, right, for the ID.
Oh, right. So it's kind of interesting because author also not sure why this happens. Like they acknowledge that if you only use I or only use D, or you actually use ID, sometimes it will help, but it's hard to tell. But at least for the second experiment, the present achieves like the best score among all. Yeah, it's kind of debatable whether this two-stage is the optimal strategy to use, but at least in several experiments, this is the case. Yeah, so let me conclude this paper by mentioning this several things. So this strategy, the presents framework, actually doesn't depend on large language model or training, right? You can do this for any model, any task. But the remark here is, the key insight is because the whole algorithm is designed based on the intuition we have for the large language model pre-training. That is, the loss kind of drop exponentially before and then plateau out later in the pre-training stage. So probably this is only suitable for this kind of large language model pre-training. So right, if you just look at it as like variable, then sure, there's nothing specific for large language model for training, but the novelty here is this is model driven, so the whole algorithm is designed based on this intuition, right? Okay, so this is the third paper, and the final one. Okay, so maybe I can stop here for now. Are there any questions? Because if not, I'm going to talk about the final paper. Okay. So the final paper is called LAVA, the learning-agnostic data attribution. I will admit this is an math-heavy paper, and it is not necessarily. I might not able to be 100% clear at every details, but I'll try my best to give a high-level intuition for this, because it is based on like unknown transport theory, linear programming, perturbation analysis, those kind of stuff, and which might take like another presentation to dive into every details. But I will stay at high level, and if you're interested in any details, just feel free to stop me, and I'm willing to explain more. Okay, so here is the setup that also consider. So basically you have a space of examples. Here, previously we only talked about like X, Y, or Z because we don't really care about the labels for large language model. But here we actually care about labels. So let's write everything out explicitly. So the space of examples consists of a feature and a label. And this label is multi-label, so it is like an indicator vector. And for each label, it may correspond to like, or multiple entries might be one. Okay, so this is like something called multi-label setup, which is quite general, but intuitively you can just think of, okay, this is just some label. Okay, so this is the number of different labels. And also I use Z for training examples, Z prime for test examples. And here, because we don't necessarily know the learning algorithm, so at least we know, okay, maybe you have some training data sets, DT for training, and some validation data set, DV for validation. Okay, and then we further assume we have a labeling function for DT and DV. So it's kind of interesting to distinguish them separately, because also consider the case that maybe a validation data set is kind of out of distribution or not necessarily the same distribution as the training data set. So we actually have different labeling functions. So basically it just says that, okay, the data on the training data set consists of xi and yi, where yi comes from some labeling function, ft of xi, right? And same for the validation data set. Okay, so what's the goal here? The goal here is to propose a learning algorithm agnostic data evaluation method. So what does this mean? This basically means we don't necessarily know the learning algorithm, but we still want to define some notion of influence or evaluation for the data. Okay, so you may ask, okay, how is this even possible if we don't know the learning algorithm? So the high level intuition is that if we all we care about is, or the influence we care about is based on validation and training set, or the model performance on validation and training set, then we can actually define some sort of distance measure between two data sets. And interesting enough, this distance measure between two data sets can characterize the performance of any model. Okay, this may need some caveat, because okay, this cannot be actually any model, but it needs to be somehow smooth, depends on the data sets we use. But yeah, assuming the learning algorithm is kind of good enough to not behave too wildly, then the distance between two data sets actually characterize the performance of the model learned. Okay. Then what's the influence? Influence will just be the gradients of that distance measure with respect to each data point, right? So intuitively speaking, if you have the distance, that right now let's just think of distance can characterize the performance. So if the distance is large, then the performance is bad. Okay. Then the influence will just be, okay, if I tweak one data point's weight, let's say I add another data point, okay, if I duplicate one data point, then somehow the distance increase. Now I know that, okay, this is the influence, right? The gradient is the influence of this model, because if I emphasize the weight for that data point, then it's made the distance become larger, suppose, then the model behaves more badly. The performance drops. So I can calculate the gradient. If I can calculate a gradient, then I know that what's the infinitesimal change if I made to that data point, what's the distance change? Namely, what's the performance change of the model? So we can use the gradients of that distance to measure the influence of the model. This is very important intuition because it will become like very math heavy after this. So I hope everyone grab this intuition. Any questions at this point? Okay, so let's proceed. The first question is, okay, how to measure data sets this distance? A very simple idea is the follows. The starting point is by noting that we can associate discrete measures for two data sets, or okay, for data sets. The intuition is very simple. Let's say we have n data points for one data set. What's the most natural discrete measure for this data set? I put 1 over n mass at each point, right? So this is exactly what I did. This is the Kronecker delta function. So it will become 1 if xiyi equal xy, right? So basically it means if this is xiyi, then this will become 1, and all other delta will become 0, so it will become 1 over n, right? So at every xiyi, the probability mass will become 1 over n. And for other xy not equal to 1 of the xiyi, the probability mass will be 0. So intuitively, I just put like 1 over n mass at every data point. Okay. And the same thing can be done for the validation data set. Then probably at this point, you know what I'm going to do. That is, I'm going to use optimal transport, right? Optimal transport, or the Earth's movement distance, can measure two distributions distance, right? So intuitively, what optimal transport is doing is look at two different probability measure. How can I move the mass I have to match another probability distribution? So I have one original one. How can I move it, or how can I let's say perturb it, and that it looks exactly like another probability measure, and the movement here correspond to some cost function. So let's say you want to move one point z to another point z prime, then the cost is described by some cost function c z z prime. Okay, and here this is just integrating or consider any possible movement. Pi denotes possible let's say transportation plane for that probability measure. And intuitively, if this is like all features, like z and z prime consists of only features, then perhaps the natural thing to do is you use like Euclidean distance, right? You want to move one feature vector to another one, then the sensible thing to do is you use Euclidean distance to measure that distance. But now z contains what? Z contains the labels, right? Okay, so what's the distance between labels, like between two indicator functions? So this is what the author referred to non-conventional hierarchically defined Washington distance. They basically take into account of the difficulty of measuring the distance between indicator functions or labels. So what I did is very simple. Let's say I want to move a data points pair, like feature and labels, and another feature and another label. I want to calculate the distance between these two, or cost, if I want to move this point to this point. Then the first thing I do is, okay, I calculate the Euclidean distance between features, which is probably the most natural thing to do. But what about labels? You cannot really do Euclidean distance between labels, and it really doesn't make much sense. So what they did is they look at the Washterson's distance between two conditional probability measure conditioned on last labels. So this is where the hierarchy comes from, right? This is an hierarchical Washerson distance, which depends on the cost, where the costs also depend on the Washerson distance. So like intuitively, basically this means that, okay, I don't know the labels distance, but at least I know I have a data set, so I can condition on that labels and see, okay, if I condition on that labels, what's the condition probability? And that induce a conditional probability distribution. And then I can measure these two different conditional probability distribution, right? Condition on these labels.
Now I have a question here. So, if imagine like if we have two data sets,
right?
Where the second data set is derived from the first data set by so basically you look at all the samples within the same label, right?
Right.
The same binary vector. And like for this data samples with the same label, you shuffle oh, okay. So it's okay, I see. That doesn't change anything. Yeah, I was trying to understand like because like the second part doesn't depend on x, right? So like the second
True.
part of
The second part only depends on y and y prime, right? So
Right.
for, let's say I change it to y prime prime, then
Uh-huh.
I can pre-calculate another like conditional probability distribution on like multi y prime prime. Then I can just use
Right.
it like whenever I encounter this. So
I see.
right, this part only depends on y, and this part only depends on x.
I
Or
see.
okay, this part only depends on y and the data set, right? It
Uh-huh.
does not depend on individual x. So this is how we measure the labels distance.
Right. So yeah. So and like if you think about this, so yeah, maybe I'm wrong, but basically like because you have the summation between those two, right? So maybe you can decompose the integration into two parts, like one integration plus another integration. So would it be the case that if you basically do some shuffling between the x and y, I mean, for example, you fix x and you shuffle the label among the data points, something like
Right.
that, would you, I mean, would you get the same distance?
No, I don't think so. I don't think so.
Mhm.
Right, because if you shuffle the labels, then basically these two conditional probability distribution will be different, right?
I see. Okay.
Right. So let's say x, like there are only 2 points in the original TT.
Mhm.
X1, Y1, X2, Y2, right? If you shuffle them, then the conditional right, if we are
Right.
considering
Yeah, that's true.
if we measure them, yeah.
Yeah.
Sure,
Okay.
they are different.
Yeah. Okay.
Yeah. So basically what the author proposes, or actually this is not what the author proposed. This is something well studied, or okay, it's already studied, and it can lead to some nice theoretical results. So I think that is one reason why they choose this distance. But this is something that is known in the literature, so not just something crazy author just define themselves. Okay. So yeah, so this is kind of like math heavy, but well, what's the point? The point is okay, now we have some intuitive, intuitive distance matter between two data sets. And they also propose to use this distance to characterize the model performance as we guarantee, right? So this is our original intuition. We can use this distance to describe or to bound the model performance. And to do that, I will need to tell you something, tell something about linear programming. So basically, the underlying theory of optimal transport is based on linear program. And probably you already know this, but unknown transport can be formalized as linear program. So yeah, so the whole theory is based on linear program. And here is just some general facts about linear program. So linear program is basically just like some minimization, there's a minimization problem of some cost. This is the linear cost function and subject to some linear constraint. I bet you are all familiar with this. And something you might not be familiar with is the duality. So here, the dual of the linear program is just some other linear program you can derive from the original linear program, which we call primal. And the nice thing about the duality is that dual linear program will gives you the same objective value. So this is one fact. I will mention it later. And another fact is something called perturbation analysis. So this is very subtle, but I hope you understand this. So I will explain this in detail. So the idea is it's possible to perturb parameters within the perturbation radius in the primal constraint. Okay, so what's hold this? Okay, let me draw. For the parameters in the primal constraint, what's the primal constraint? Is ax less or equal to b. What's the parameter? Parameter is the b. Okay, so we could perturb b on the right hand side of the constraint without affecting the dual optimal solution. And know that the dual optimal solution does not mean the dual optimum objective value. Okay, so what does this mean? This means if I perturb b small enough, sure, the final cost might be different. Okay, that's fine. And from duality, we know that the derived dual linear program will achieve different objective value because the primal changes, right? But you know that the solution here is these variables value. So if you change b and something will change in the dual, actually the cost will change in the dual, but the dual variable will not change. Okay, so if you compute the dual solution, namely, let's say you derive a dual that is something like maximum over y. Okay, so y is the dual variable. You don't need to care about that, but you just know that there's some dual linear program which with different set of variables, let's say y. And you can solve that, and that will give you the same objective value, but not necessarily the same solution. So the solution here means x or y. Okay, so here, I mean, if you change b, namely you will change something in the dual problem. Sure, the dual objective value can change, but the dual optimal solution, namely the y, will not change. Okay, so actually you have a very robust dual solution for this dual program for perturbation analysis, from perturbation analysis. This is a general fact from linear program. So basically, what you can do is you first derive the dual from the primal, right? You solve the dual, and then you are interested in, okay, what's the primal objective value you change if I change b, right? Then you don't need to actually solve everything again. You can just change b. Okay, you can just change the primal's cost with respect to the b, because if you change b, the cost in the primal, the cost in the dual will change. So you just need to change the cost in the dual, then you can use the same dual solution. You multiply that with the new cost, it will give you the new optimal solution, optimal objective value. So it is very robust, and you don't need to recompute everything again if you just care about some slight changes. And these changes need to be in some radius. So yeah, that's just the one core feature for linear program. Any questions? I hope you grab the idea. So this can be a bit hard to imagine, but the overall idea is you don't need to recompute the overall objective value if you just care about the sums changes. And in fact, you can also compute the exact gradients because you know the exact change, right? So the gradient is exact within not infinitesimal changes, but within the whole radius. Within the whole radius, the gradient will be the same, basically. This is another nice thing of a linear program. So the highlight is the omnidirectional transport can be modeled as linear program, and with some caveat, that is, you need to use entropy regularization. It can be solved efficiently, and it's also possible to compute the perturbation efficiently. Okay, and with perturbation analysis, you can also get exact gradients. Okay, so if you so now you have a lot of intuition lingering around, and you might already figure out like how to put them together. Like when perturbation, you have gradients, you can compute them exactly. You don't need to know the you don't need to compute everything again, and it's kind of robust. Okay, so if you put everything together, then we have the follows. First, let me formalize. The perturbation is nothing fancy. It really just means gradients of the objective value, right? So the objective value is the distance, right? So here, let's highlight that optimal transport can be modeled as linear program. So the objective value of that linear program will be the distance, right? The distance is this distance. So effectively, this will be minimization over some linear program. And at the end, if you solve the linear program, the objective value will give you the distance. So the gradients of the objective value is what we call perturbations, okay? Or actually the influence we care about. And it corresponds to changing the right-hand side of the constraint, right? Recall, constraint is something called like x less or equal to b, and this is the right-hand side. And for linear program, the constraint is all possible transportation plane, and it can be somehow formalized as linear constraint. Okay, I just write this out, but don't be afraid. This is just the transport plane, and the right-hand side corresponds to mu t and mu v. So you can perturb the probability distribution. Okay, this is the intuition. The right-hand side of the constraint corresponds directly to the probability distribution. So what does that mean? That means the gradients with respect to the right-hand side of the perturbation of the constraint is just this, right? You care about the objective value change when you perturb the weight a little bit on the right-hand side. Okay, so there is some slight remarks. In practice, we do not actually allow any kind of change. We kind of want, after we change that weight of the discrete probability distribution, we want the overall sum still sum up to 1. So it is still in probability distribution. So we care about something called calibrated gradient, but it's very minor, but worth noting. Okay, so combining this with the theory of linear program, we know that it's possible to characterize the actual change of WC within certain radius. Right. So recall what we just said for the linear program. We know that we can access the new objective value if we change slightly the right-hand side. And how can we know that? Okay, maybe we are, I'm not being explicit, but how can we do this is by computing the gradient. Because the gradient is, because basically everything is linear. So if you have a gradient, you have the exact change. That's the intuition. So it's possible to calculate the actual change of WC within a certain perturbation radius. So if you perturb the mass in the probability distribution a little bit, you know exactly how WC will change. And the underlying computation is done by computing the gradient. Okay. And furthermore, these gradients are efficiently computable if you are using entropy regularization. And so now you might think, okay, so combining all the intuition we have, we know distance characterize the will characterize the model performance, so it can act as an influence. And we now know how to characterize that change, so it should correspond to the influence. So now the problem really is, you guarantee that it is valid within some radius. So how large is the radius? If it is very small, then probably it's not very useful. So this is some empirical study for the perturbation radius. So empirically, the radius is kind of small, like 5% to 25% of the probability measure of the data point. So it's not like 5% of the overall probability mass, that is 5, 0.5. But it's actually only 5% of one data point's mass, that is 1/n. So it's actually very small. So we can only predict the change of WC from partially removing or adding data points to the data set. So, okay, it's still slightly better than influence function, because influence function can only do infinitesimal. But here we can do like, at least the epsilon is, let's say, 1.05 or 1.25. But like empirically, the relative error seems acceptable even if I remove everything. Like here, this is the green dot is the actual change, and the dash line, the black dash line, is the predicted change. Like it is just linear, and it seems like the theoretical accurate prediction range, namely the perturbation radius, is very small, but the relative error stays pretty low. Like if you add exactly one more, or you duplicate the points, and the relative error is just like 2%. And even in the bad case, it is like 15%, kind of, okay, acceptable. Okay, so with everything clear out, I want to kind of state the exact theorem they have. So why do we care about changing in the distance? So here is the theorem they prove. The guarantee of the distance actually characterize the model performance. So this is kind of like the generalization bound, but it's characterized by this hierarchical defined Wasserstein's distance. So this is very informal. Let's take a look. Given any smooth enough model F trained on the data set, training data set, and given some loss function, under some condition parameterized by epsilon k n, don't need to worry about that. We have the followings. So you see, this is the expected error, right, on the validation set. This is bounded by the expected error on the training data set plus some factor times the distance and some deviation term. So let's break this apart. So first, if the model is good enough, then we know that the training error should be relatively small. So okay, this term should stay small. Okay, the first intuition we have. The second one, when all assumptions on set are satisfied, then the last term is small. Namely, if they are all smooth enough, they are all parameterized by k and m, then this will be small enough. Okay. So that's fine. This is like theoretical result. Okay, so what does that mean? That means it's possible to use WC, the Richardson distance we care about, to bound the validation loss. Right, so this is like exactly what we guaranteed. Like we can use the distance, like somehow bizarre, funny looking distance between two data sets to bound the validation loss. So if the distance is large, then the validation loss is large, then it's very bad. So we know that if we change slightly the data points, if we know how can that affect the distance, we know how can that potentially affect the validation loss. So we know that model behavior is characterized by the Richardson distance. So we can view how changing the weights of one data point changes on the distance as the influence. So that's the overall justification of why we care about WC. It is because of this theorem. Any questions? If no, I'm going to briefly talk about the experimental results and also some comparison between this method and other well-known, let's say, influence function. I know it's kind of hard to grab, but the overall idea is we invoke linear program theory, and that is because our distance we care about depends on optimal transport, which in terms depends on linear program. And okay, this distance characterizes the model behavior, so we can use it as a surrogate to get some influence. And if you look at this in detail, you will find out that the only assumption we have for the model learned is model is kind of smooth enough with respect to dt and dv, so it cannot be just like arbitrary model. Like it's really like learning algorithm agnostic. Like if my learning algorithm just randomly output one decision model, then sure, this will not be the case. But if it is somehow smooth enough, the algorithm behaves kind of in the sensible way, then we can do this. So here's the advantage if we compare to the traditional influence function. So you see that influence function is only valid for infinitesimal change with respect to data weights, while the perturbation of linear program is exact, at least within a certain radius. This is from perturbation analysis. And moreover, it enjoys some interesting property from the computational standpoint. The first one is theorem 1 is for a non-regularized version. Okay, so here theorem 1 WC, if we want to solve it exactly, it's not necessarily efficiently solvable. So if you still recall, when we want to solve an optimal transport by linear program, we need to use something called entropy regularization. However, with small enough entropy regularization, the computed gradients will not give us the actual influence for the non-regularized version, but we can somehow reconstruct the ranking between the influence exactly. This is an interesting theorem. I encourage you to look it out, look it up on the paper. It's very clever. Like they basically says that if you solve the entropy regularized version, you'll get another like entropy regularized influence. That will not necessarily be the non-regularized version influence, but if you take a look at the difference between two influence, they are basically the same. So you can reconstruct the rings. And like most of the time, influence, the absolute score of the influence doesn't mean anything. Like the relative ranking is what we care about. So that's something very interesting. Like you can reconstruct the ranking exactly. Okay, so finally, I'm just going to talk about the experiment, and basically their experiment is summarized in this plot. So let me briefly talk about them. they have 6 different baselines, 6 efficient baseline: lava, influence function, KN, Shapley, tracing self, tracing clean, and random. And on 4 tasks, and they are done by done on the Ethereum side with 10,000 data points. And so for the first one is the backdoor detection. So the goal of the backdoor detection or backdoor attack is to inject some backdoor examples. So whenever the model sees like backdoor examples, presumably having some, let's say, watermark or triggers, it will predict a wrong label. Okay, and the goal is to use the influence to figure out what are the backdoor examples. So this is the backdoor detections. So here we see the detection rate is very good for lava. It stays on top, namely when, let's say, when we only look at the first half, it's already detect or already figure out nearly 100% of the backdoor examples. And here is the attack success rate. So if you store away, let's say, slightly before, like a quarter of the data, the success rate is already drops to, let's say, 50%, while other very well-known method, let's say influence function, still stays like around 100% success rate. So even sorting out the top quarter of the examples, influence function cannot detect backdoor examples, while lava can. And a similar story can be told for, let's say, poison detection, noisy feature detection, noisy label detection. And I probably won't go into detail because I'm a little bit out of time. But yeah, it's the basic message here is for all experiments, all tasks, detection rates for lava outperforms other methods, while the attack, let's say, success rates, confidence are all the lowest, while the model accuracy for the noisy feature and noisy label detection task, lava performs the best. So basically here, while looking at if I store away quarter of the noisy data reported by lava, then our model accuracy can already bump from 70% to 80%, while other methods, because you are throwing away too many good samples, it starts to drop. So lava is actually able to store away noisy features data. And the same story for noisy labels. Yeah, so that's basically all of the presentation. Any questions?
Oh, by the way, can we want to show the reference page?
Sure. Yeah, so yeah, 4 papers. I didn't include like other, let's say, influence function because that'll be too much, I guess. But yeah, 4 papers are here. You can look it up if you're interested.